Hello, welcome to the week before spring break. This week is going to be your assessment week on mirrors and light. So we're going to do a quick review that I'm going to kind of walk you through a little bit. If you would like to, I will have a practice quiz as part of this video as well. Both things can be found in your packet. And then you're going to have a short answer portion of the quiz where you're going to actually draw out the mirror diagrams, and then there'll be a multiple choice piece in Schoology. You can work on them at your own pace. They just need to be turned in by Friday at midnight. Okay, so just a quick review of light to start. The equation that we're using for light is our C equals frequency times wavelength. C is the variable for the speed of light. So C is our 3 times 10 to the 8th meters per second, and that's on your equation sheet if you have forgotten it. In order to calculate frequency, you need to have both C, which we do, and you need to have the wavelength, but the wavelength has to be in meters. Okay, so you are going to have to set up a conversion first. We have 550 nanometers, and in 1 nanometer, there are 10 to the negative 9 meters. Okay, so you're going to have to multiply 550 times 10 to the negative 9. That will get you your wavelength in meters, and from there, you will be ready to work through your C equals frequency times wavelength equation. Number 2, same idea. You're going to look at your two wavelengths and you're going to predict which one has a greater frequency. A quick reminder with your equation, frequency and wavelength, they have an inverse relationship. So if you are looking for a higher frequency, you are looking for the one with a lower wavelength. And then finally for number 3, how many meters does light travel in a year? There's 2 ways to solve this. You can use an equation, V equals delta x over delta t, because light travels at a constant speed of 3 times 10 to the 8th. You just have to make sure your time is in seconds. Or the easier way to do it is just to set up a conversion. You are going to take the speed of light, 3 times 10 to the 8th meters per second, and you are going to convert the meters per second into meters per year. That you'll have to do using hours and then days, from seconds to hours, hours to days, and days to year. For the station, the review of mirrors, I have a magic mirror. It's a hologram mirror. So I'm going to pause the video, I'm going to show it to you quickly, and then we're going to kind of go over what you saw with it. Okay, here is my magic mirror. It is a Mirage hologram. So what I have here is just a little guy that is sitting right there. It's a little pig. The question is, can you touch it? And if you were here in class, you would just go up and you would try to put your hand in there. And notice you are not able to touch it. That's because it's not actually there. It is just a projection. It is a projected image. The actual pig is on inside the mirror. There's a concave mirror in there. There's another concave mirror on the top. You have light bouncing off of multiple mirrors, and it bends everything or reflects everything so that it makes this projected image right at the top. It is not actually there. It's down below, but you can see it. Back to the board. Look at the object in the black disc and try to touch it. Can you? Why not? You cannot touch it because it is not there. And then here's the difference. This first part, we are looking at the difference between a real and a virtual image. Okay, this drives people crazy. What I just had, a hologram, I could not touch it. Okay, so people think, oh, that must be a virtual image. But technically, it's a real image. So what type of image can be projected? If you go back to the first page of your note packet, if it can be projected, it is a real image. So the Mirage hologram image, it's projected, so it has to be technically a real image. Inside of the mirror, it must be a concave mirror. If you look back, the reason for that is on the front page, only concave mirrors can make real images. Convex cannot. It scatters the light in line with a focal point behind, so it can't pinpoint all of those light rays in one spot and then project it. It cannot be a convex mirror inside the disc because convex can't make real images. Only concave can, convex cannot. From there, as you move into the back, you are going to do one of each type of mirror with math, and then you're going to do a diagram from each as well. The thing that you have to make sure that you remember, when you are doing the math, you have to make the focal point negative for a convex mirror. So for number one, you've got a convex mirror with a focal length of 2.5. You have to make it a negative 2.5 when you do your math. So for 1 and 2, you are going to solve for it using equations. And then question number 3, you are going to do one of each type of diagram. The F, the P, and the HO are going to be the same for each type of mirror. The only difference, remember when you're setting up your diagrams, convex will put the focal point behind, concave will put the focal point in front. Okay, so you have to be careful, measure everything out, and then run your lines. Okay, take a pause here, and please try to answer questions 4A through D. Hit pause on the video, try to answer them yourself, because you may see some of these in multiple choice, and then check them to make sure that you have the correct answers. If the F is negative 2.5 centimeters, what type of mirror? Well, all we know is that the F is negative. Only one type of mirror has a negative F, and that is convex. If the image height is smaller and upright, what type of mirror is making it? That's the hallmark of a convex mirror. If it makes something that is always upright and smaller, it's on a convex mirror. If the image height is inverted, if it's upside down, only one type of mirror can do that. We saw that concave mirrors could turn things upside down. And finally, if the image is real, what type of mirror is it? Only one of the two mirrors can make a real image. Once again, it's concave. All right, so you are finishing up this review. That is the only thing for points homework-wise. In addition, you have your 2 parts of the quiz, the short answer piece where you're drawing them out, and then the click through the multiple choice. In class, we also are doing a mirror practice quiz. So I'm having everybody work their way through. We take about 10 minutes or so, and we work our way through. So if you would like to try that before your quiz, if the review was not enough practice, then I'm going to have you pause this video, and then I'm going to have you work your way through the practice quiz, and then come back to it. I'm going to work my way through it so that you can grade your own practice quiz and see how it is. So I'm going to pause for just a second. Okay, I am ready to go. So pause and try the practice quiz if you feel like you'd like a little extra practice before you actually do one for points. So I am on page 6 in your mirror packet. Once again, you do not have to submit this for points, so please don't try to find a submission for it. All right, so we have 2 sets of mirrors. The first one is concave. I have a 1.5 centimeter tall object. It is placed a distance of 3 centimeters away from a mirror with a focal length of 1. It is a concave mirror, so that F is going to be positive. Okay, you are going to solve it 2 ways. You're going to measure Q and HI, and then you're going to solve for Q and HI using your equations. Okay, so first thing you have to do, take your protractor. You've got to get a focal point measured out 1 centimeter in front of the mirror. So as I measure mine out here, that is going to be my F, and it is to the left in front of the mirror for concave. I need to place an object 3 centimeters in front of the mirror. And I need that object to be 1 centimeter tall. All right, so you have measured out 1 centimeter to get your focal point, you have measured out 3 centimeters to get the object, and then, whoops, this should be 1.5 centimeters tall. Sorry, I need to make him a little bit taller. Okay, once you have that, you are ready to run your lines. So quick reminder, first line goes straight until you hit the surface of the mirror. It then bounces off through the focal point. Second light ray goes through the focal point on the way to the mirror, and then it bounces back straight. The intersection point. We are going to measure 2 things about that. You are going to measure the HI, that is the distance from here to the intersection point, and Q, the distance from that intersection point back to the mirror. Okay, you just lay your protractor right there. So you're going to actually measure it from here to here, put your answer there for Q. It should be positive because it's in front of the mirror. And then you're going to lay your protractor right here, measure the height of it from there to there, put your answer right here, and it should be negative because it's pointing downward. And this is a real image because it is in front of the mirror. You're also going to do the same thing, except you're going to use equations in order to do it. So you're going to take your 1 over f, 1 over 1, equals 1 over p plus 1 over q. You are going to subtract the 1/3. You can turn it into decimals if you like, so we'd have 1 equals 0.33 plus 1 over q. You're going to subtract the 1/3 to the other side, and that, if you put it into decimals, is going to be 2/3 or 0.67. That is not q, that's 1 divided by q. So I got to do that switcheroo. I have to cross multiply and divide. If I take 1 divided by my 0.67, I end up with q as 1.5 centimeters. From there, I'm ready to solve for HI. HI over HO, 1.5, equals negative Q, negative 1.5, over P, which was 3. So I'm going to cross multiply and divide, and I end up with a height. It's going to be negative because it's pointing downward, and I got about 0.75 centimeters for that. All right, so that is a quick review of concave. We're going to use those same numbers, but we're also going to do it for convex. So the P is going to be 3, the height is going to be 1.5, and the focal point is going to be 1, but because it's convex, you got to throw a negative sign on there, which means when you measure out the focal length, you have to measure behind the mirror. Okay, so I need to measure 1 centimeter behind the mirror, and I need to mark it as F. I then need to measure, I need to measure 3 centimeters in front of the mirror. And I need to get an object that is 1.5 centimeters tall. Okay, so 1 centimeter, 3 centimeters, 1.5 centimeters. Okay, same thing. I need to run my 2 lines. I'm going to go straight until I hit the surface of the mirror, and then it bounces off in line with the focal point, but it's behind the mirror. So light doesn't actually get back there, we know that, but we have to just draw it like it does. Second light ray lines up with the focal point. If you could get through the mirror, it would go through the focal point, but it can't get through the mirror. It stops at the mirror. So I line it up. If I could go through the mirror, that's a terrible line, it would go all the way down through the focal point, but once it hits the mirror, it bounces back straight. Where they intersect is going to be our image that we see in the mirror. You need to measure 2 things. You need to measure HI, that is the height of your guy right there, and you need to measure Q, which is the distance to where the image shows up. Okay, you're going to put your Q and your HI right there in the boxes, and then you should know that this is virtual because it is behind the mirror. we don't actually have any light going behind the mirror, we just have to draw it like it does. That's what makes it a virtual image. From there, to do your equations, only difference in the math from up above is you have a negative sign. So we have 1 over negative 1 equals 1/3 plus 1 over q. If you prefer decimals, we've got a negative 1 equals 0.33 plus 1 over q. This 0.33 subtracts to the other side. That makes it more negative. So we have a negative 1.33, or negative 1 1/3, equals 1 divided by q. I gotta do that switcheroo. I have to take 1 divided by the 1.33, and I end up getting q is a negative 0.75 centimeters. From there, I'm ready to find HI. Okay, HI over HO equals negative q. Negatives also, or q is also negative, so those flip to positive, divided by p. I need to cross multiply and divide, and I should get a height, it's small, of 0.375, 0.38, somewhere around there. All right, so we have done one of each type of mirror, both drawing out the lines and solving for the math. Okay, that's your practice quiz, so you'll need to be prepared for that. The last couple there, once again, pause the video, try it on your own, and then double check it. You might see some of these show up in the multiple choice. An image that occurs when the actual light rays cross in front of a mirror and it can be projected, that is a real image. When the focal length is negative, you have this type of mirror, that's convex. The definition for what is object with a reflective surface? That's a mirror. And when light changes direction by bouncing off an object, that's the definition of reflection. Those two I think you can find in your mirror equation notes from week 5, and then the other guys will be kind of on the front page of your note packet from week 6. So I hope you feel prepared for your quiz. Once again, you do not need to submit the practice quiz. You only need to submit the blue page in the packet, which is the light and mirror review. That will get you points, and then you will work your way through the short answer, drawing out the mirrors. You'll submit that, and you'll work your way through the multiple choice piece of it as well. So thank you. I hope you do well in your assessment.